Hello. So we just finished the chapter in our textbook about crystalline structures, and we talked about crystals as being a combination of a lattice, which tells us about the symmetry of the crystal, and the atomic basis, which sits on the lattice. We went through some of the basic crystal structures that are common in metals, and we wound up talking about diffraction as a means to measure the crystallinity, the lattice parameters, and the behavior of that crystal. and now we're going to talk about defects. And in particular, defects in crystals. So defects in crystals, you can think that defects are really what makes crystals useful. If we were limited to only working with perfect crystals, there would be very few things that we could do. I mean, after all, you have a lattice and that's fixed, and the atomic basis and that's fixed. And what can we do as engineers? Well, not really much. So materials engineering is really about being able to introduce defects in crystals. So when we think about these, what I'd like you to think about is I'd like you to start to think about solidification, right? So if you have some system, and systems are boxes, as we all know, we have our box and we have all liquid in that box. Well, we cool that box down to below the melting temperature, and what happens is we start to get little nuclei of small crystals that form. Now, because these nuclei are all dispersed in this liquid, they don't see each other and they don't know about each other. And as they start growing, they start getting a little bit bigger. We look at them and we realize that they all have, a different orientation to them, a different arrangement. And what that means is that when we get to our final solid, we're going to wind up with a different series of crystals, each one with the planes in a slightly different orientation, right? So if you think of these as, say, a particular family of planes, say this is the 111 family of planes. Well, this 111 family of planes is going to have a different orientation. And in some cases, for example, say, or change colors here, say here, we have a fairly large difference in the orientation. And this would be called a grain boundary. It's going to be called a high angle grain boundary. And that's a form of defect because our total system is no longer a single crystal but a bunch of polycrystals, and we have grain boundaries between them. But we can also have crystals and boundaries that are very close to each other. So for example, if this is another boundary, we could have something that is, say, like this. And these planes are very close to being aligned, but not exactly. And this would be called a low angle grain boundary. And I'm using GB to specify grain boundary. The high versus low angle has to do with the angle between the planes, the misalignment. So for example, a low angle grain boundary would be something like this. And if we look at the alignment, they're actually pretty close to each other. You know, low angle, that angle is less than around 10 to 15 degrees. And that makes it a low angle boundary. Anything greater than that is referred to as a high angle grain boundary. So grain boundaries are one type of defect. And we talked about these at the end of the last lecture, so you know that these grain boundaries, they are important, and controlling the grain size is important because the mechanical properties or diffusivity properties, thermal properties depend on grain size, and the boundaries can be engineered. So we can make boundaries such that they impede dislocation motion, and we'll talk about dislocations later, but basically I'm saying that they will make it more difficult to have plastic deformation. We can make the grain boundaries so that it's easier to have plastic deformation. We can make the grain boundaries so that they're thermally insulating, or we can make them so that they have a whole different set of properties from the bulk crystal. And that's one form of defect. Now, another thing that could possibly happen is, let's think about the solidification process and solidification, and say we have a wall, right? Well, a wall here, and we know, just from growing ice in our freezers, that when you are solidifying, you don't form crystals in the center, you actually form crystals on the surface. And if you look, you open up your freezer while you're making ice, you'll notice that there are crystals on the top of the water, and you'll also see crystals on the edges of the ice tray. So what happens is you get nucleation on the walls, and then they will grow out from there. So we have interfaces that are associated with the crystals as they form, and the surrounding areas. So these interfaces are also types of defects, whether you're thinking of an interface between, say, a crystal and the air, or a crystal and a surrounding material. So this nucleation from the center, we call that homogeneous nucleation. And nucleation from a wall, we call heterogeneous nucleation. And we'll talk about this in more detail when we get to chapter 11 in the book. But right now, I just want you to think about the possible defects that form. And if you want to think about how these grow, well, these grow because we have our liquid, and we have atoms that are in this liquid that are relatively disordered, and as it cools down, atoms are going to attach themselves to the surface, and they're going to attach themselves in this regular pattern. But you can certainly imagine, as you have, say, solid and liquid up here. So our solid has atoms arranged like this, and this is not a closed packed structure, but an atom will come down and it's going to sit here. Another atom's going to sit here. Another atom's going to sit here. We have growth this way of the solid into the liquid. We can certainly imagine something else might happen. For example, instead of going row by row, you might get another row forming up here. And as atoms come and they attach themselves, you'll have atoms grow, and you'll wind up with missing atoms. Right? These are called vacancies. Vacancy. You have to overlook the spelling there. Vacancy. And these vacancies, we will draw little dashed lines. Those can also be types of defects. Perhaps the liquid also has impurities, right? Maybe it has some small impurity atom, right? Well, that impurity atom, that can come down and it can sit, say, here. And other atoms that form around it are going to get squeezed out a little bit by it. That impurity atom, it can sit between the atoms. If the impurity sits between the atoms, then we refer to it as an interstitial defect. So basically we have some impurity and it's sitting in between them, and it causes some type of strain to the atoms around it. If, however, the defect sits on a lattice site, for example, here, or not lattice site, sitting on an atomic site where we should have one of our open orange atoms. We have a closed orange atom site, called atomic, sitting on an atomic site. Then it's called a substitutional defect. So basically, interstitially is talking about there being some interstitial site, and we'll talk a little bit more about that later on, I guess, Monday. And substitutional is when the defect sits in place of one of the originals. And sometimes those defects are smaller and sometimes they're bigger than the host lattice or host atoms. And when it's smaller, then you wind up with atoms being kind of squished in and compressed. If it's larger, then it's going to wind up pushing these atoms out. But regardless, the size difference is very important for creating local strains. And we know from talking about bonding that if the number and nature of the valence electrons are different, then we'll wind up with an electronic effect. So for example, maybe this atom has extra electrons in the valency, and that's going to give electrons to the neighboring lattice that can, say, increase electrical conductivity, for example. So that's another type of defect. So when we classify defects, we talk about them relative to their dimensionality. So zero-dimensional defects, these are called point defects. Point defects, for example, are vacancies, missing atoms, interstitial defects. Interstitial defects are sitting between atoms on the sites, and substitutional. We can have one-dimensional defects, and the most common type of one-dimensional defect is called a dislocation. And those are basically defects that, and we're going to talk about these in much more detail in the future, but those are basically defects that act like long, if you want to think of it as threads, and they are connected defects that are going to thread through the crystal and start on one surface and thread through and make it to the other surface. Or sometimes they will be in a crystal and they'll move around and they'll close. You actually have these closed loops. And if you look at them in the microscope, you'll see these look like closed loops in your material. And dislocations are extremely important, and the reason we're going to talk about them more is they're important for plasticity. So these dislocations are fairly common in metals, and this is what makes metals ductile, but they're extremely uncommon in materials that are primarily covalently or ionically bonded. And that's why those materials are brittle. So glasses are brittle because you don't get these dislocations as a means for plastic flow, and dislocations are much more mobile in, or they exist in metals. Therefore, metals are ductile. We can have two-dimensional defects. These are grain boundaries. Interfaces, surfaces. So the interface between, say, our material that we're interested in and the mold wall that it grows in, between the material and the outside world, and between different grains within the same material. And lastly, we can have three-dimensional defect. And these are typically larger. They can be voids, and they can be, for example, bulk inclusions. Imagine, for example, you're casting an iron part, and you pour molten iron into a mold that's made out of sand. Well, if some of that sand breaks free and you get a little piece of sand that is stuck in your metal, that's going to be a three-dimensional inclusion that is going to have a fairly significant impact on either the mechanical or the surface properties of that metal. So let's talk a little bit about point defects. Well, I said point defects. We can talk about vacancies, and we can talk about interstitials. In the case of vacancies, you know, if we talk about, say, a crystal, and let's say there's a vacancy here, what's going to happen? Again, my drawing is terrible. Let's say there's a vacancy right there. If we can draw lines to represent the planes of atoms, we have some type of curving here near the vacancy, and same thing as we get near it. We also have curving. So there's going to be local strain near the vacancy. There's also going to be electronic effects. And these electronic effects are because we have a site here where, for example, these neighbors were expecting to have a certain amount of charge, a certain collection of electrons near them, and that's now gone. So that's going to have an electronic effect. And that's certainly how vacancies can form. Talking about interstitial and substitutional defects. Well, interstitial and substitutional, again, there will be strain due to size effects. And there will also, again, be electrical effects. Talking about these, now substitutional defect is always going to be a different atom type. Right, so say we have a lattice and it's made up of iron atoms, and we have, I don't know, tungsten, or we have chrome that happens to be present. Well, those can be substitutional. And the reason that they're probably substitutional is they're going to be very similar in size, and they're also divalent metals, so electronically they're going to be very similar to iron. In contrast, say carbon, is much smaller than iron, and steel usually contains several percent of carbon. This carbon does not sit substitutionally, but instead it sits interstitially. And it's this interstitial carbon that changes the mechanical properties of steel, and it's what makes steel, in part, is what makes steel a much harder material than just bulk iron. Now, interesting thing about interstitials is that interstitials do not have to be a different atom type. We can also have self-interstitials. Right? And that's basically a situation in which you have your crystal structure and you've got interstitial sites where atoms can go, and you have an atom of the same type as the host material that's sitting interstitially. And that's important because this is part of the diffusion process. So in all materials, we have kind of this constant self-diffusion. Self-diffusion. And if you want to think about it, you can think about it as kind of a constant internal stirring within the material. That's happening And at room temperature, that's a fairly slow process. At higher temperatures, it's much faster. And it's this self-diffusion that in part helps with the diffusion of other defect atoms. It's also in part what results in mechanical deformation such as creep and other low temperature processes. And also, for example, fatigue. Cracks can begin to form in fatigue due to self-diffusion that leads to the nucleation of little micro cracks that will eventually grow into larger cracks and cause failure. So these self-interstitials are important for controlling self-diffusion. Now, I'm talking a lot about defects. Put that in quotes. Defects are atoms that sit in our crystal lattice that we don't necessarily want. And an alternative name for a defect is a dopant. Now, a defect and a dopant, they are the same thing. A dopant is an atom that is in our lattice that isn't part of the host, but a different atomic species. But the difference between a defect and a dopant is that a defect we typically don't want, and a dopant is an intentional defect. Right? It's something we put there on purpose. And we put that there on purpose, possibly, for example, we put carbon in, and we dope iron with carbon in order to make steel. Or we can put it in to control the electronic properties. So remember I talked about the Lewis dot structure for silicon? All right, so I said silicon has 4 valence electrons and it bonds to 4 other silicon atoms, each one of those with 4 valence electrons. 1, 2, 3, 4. A lot of drawing here, huh? 1, 2, 3, 4. And as a result, we have these closed shell bonds. Well, if we dope silicon with, for example, arsenic, well, now what's going to happen is we're going to take out the silicon and we're going to put in arsenic. Now, arsenic, though, is sitting just to the right of silicon. So arsenic has 1, 2, 3, 4, 5 valence electrons. And as a result, where we had this chemical environment of silicon, the 4 neighbors, and there, 3, 4, 1, 2, 3, there are 4 valence electrons each. 1, 2, 3, 4, 1, 2, 3, 4. That arsenic atom is going to sit here, and it's going to have 1 electron, 2, 3, 4, and the 5th electron. Well, that 5th electron does not fit into any of these 4 bonds, right? So that electron is free to move. It's not exactly free. It takes a very small amount of energy to liberate that electron and make it free. And we'll talk about that more as we get to electronic properties down in I think it's chapter 18 of the book. But nonetheless, this is an example of how doping is used to control the electronic properties. Now, all of these impurities, or these defects, they take energy, right? A vacancy, right? We said the vacancy causes local strain, and that local strain introduces energy. The electronic effects, that increase the energy as well. Interstitials, they push out the atoms around them. Substitutional defects, they either shrink or expand the lattice. So there is some energy to add defect / dopant atom. Right? And that energy, it depends on the size of the atom, it depends on the valency. On size and electronic configuration. It's relatively simple or low energy to put atoms onto sites that are the same size. So for example, copper and gold. It's very easy to put copper into gold or gold into copper. And that is in part some of the challenges in working with gold and copper interconnects in semiconductors. Also, for example, putting boron, carbon, arsenic, gallium, germanium, nitrogen in silicon. Very similar chemical bonding. These are all p-valent. Silicon is p-valent. They're very similar in size, and they're relatively easy to put in. In contrast, for example, say putting, say, tungsten in silicon. Well, tungsten in silicon is large, it has d electrons, silicon doesn't, so it's not going to sit on the silicon site. It's fairly big, it does not want to sit interstitially, it does not want to sit substitutionally. So, elements with relatively large differences in size, large differences in electrical behavior are high energy defects. Defects that are similar in size, similar in electronic behavior, are low energy. So that tells you about how difficult it is to put things in, and this brings us back to the concept of Arrhenius behavior. So remember, I'd said a few times in class that anytime you have an event, and that event has some energy barrier that has to be overcome, we can describe it in terms of the Arrhenius behavior. So in the case of the concentration of point defects, of concentration of point defects, that's also described by an Arrhenius expression. Let's say vacancies. Just for the sake of having an expression here, NV, the number of vacancies, is equal to the number of potential defects, or number of atomic sites, times the exponential of minus QV over KT. Now, QV, that's the energy to introduce defect. Vacancy energy. You could also call it the energy of formation. Energy or enthalpy of formation. T is the temperature, and K is the Boltzmann constant. And this is the general expression for an Arrhenius distribution. And when we talk about these, we typically don't know the number of atoms, right? You don't, hold a block and say, oh, this has, 10 times, 1 times 10 to the 120th atoms. That's just too large. So instead, we'll typically talk about the concentration of defects or the fraction of defects. So we'll talk about NV divided by N, which is equal to X minus QV over KT. I also want to point out the Boltzmann constant. This has to do with the creation of individual events. So for example, the Boltzmann constant and the gas constant, they're related by the Avogadro number. So this is going to be a molar quantity, this is going to be a per atom quantity. If you're given the energy to create vacancies and the energy is going to be, say like 1 electron volt per vacancy, you use the Boltzmann constant. If the unit of energy you're given is energy per mole, then you need to use the gas constant. Big trick is here, always keep track of your constants, and when you start substituting values in, make sure that whatever goes into your exponential comes out unitless. If it does come out unitless, then it means that either there is a mistake in the units being given to you, or it also might mean that you're not thinking about units correctly. A lot of times I find myself working out units, and it's like, oh man, there's a extra unit of atom, or there's an extra unit of mole that I just don't see where it comes from. And what I recognize is that, for example, someone gives you, say, oh, the energy of vacancies is 1.2 electron volt. Well, it's 1.2 electron volt per atom, and you need to carry that per atom with you in order to make sure that your Boltzmann constant comes out, or actually works correctly, and gives you a unitless expression. So making sure that the units are correct are certainly a way to keep your math correct, and a way to make sure that you actually learn the content and have a good physical understanding of what's going on. Right, so remember the Boltzmann constant, this K is equal to 8.62 times 10 to the minus 5 electron volt per atom Kelvin, so temperatures in Kelvin, and that's also equal to 1.38 times 10 to the minus 23 joule per atom Kelvin. And again, using the Avogadro constant, you can get out the gas constant from this as well. So if we think about these and we think about the a measurement of these, we're going to have NV for the temperature, and it's going to do something like this. Right, because it's exponential, so increasing the temperature, the number of vacancies will dramatically increase, and at some point you're going to experience melting because you have so many vacancies and so many broken bonds that is essentially a melted structure. Now, the math for this, let's look at this. NV is equal to n exp negative q over kt. If we take the natural log of both sides, ln nv is equal to ln of n exp negative q over kt. The logarithm of the product of anything, for example, ln of a times b is equal to ln of a plus ln of b, which means that I can write this as ln of n plus ln of exp negative q over kt. The natural log of the exponential makes those two go away. So that is ln of n minus q over kt, where the negative sign's in there as well, which I can rearrange this as negative q over k 1 over t plus natural log of n and b. So I can write it this way. And what's handy about this is that we now have, say, a response, or our number of interest, in terms of something that we can control, and we have a coefficient in front of that, m, and another constant, b. So it has the form y equals mx plus b, which is this is the equation of a line. Where m is the slope and b is the slope intercept, or the intercept of the line with the y-axis. So going over here, if I plot, let's say I measure several vacancy concentrations in one form or another, and I plot natural log of the number of vacancies that I measure versus 1 over temperature, I'll find something like this. Say, and there's going to be error bars on that, of course, because it's a measurement, and we always put error bars on our measurements, I hope. But this, then, is a straight line. And where that straight line intercepts the axis, that is equal to b, which is equal to ln of the number of sites available, and this slope is m is equal to minus qv over k. So this type of natural log versus 1 over t plot, this is inherent, it's kind of an inherent technique that you can use for dealing with Arrhenius relations. And those of you who want to read more about Arrhenius materials, Arrhenius relationships, you can look it up there. So this is something that's useful, and certainly is a good question for exams. For example, how would, given a couple points, how would you determine the activation energy or the energy to form a vacancy? It's also nice if, say, you have a couple measurements and you want to know the number of vacancies present at a different temperature. As I increase the temperature, how many vacancies are present? If I double the temperature, well, you can determine the slope and the intercept, and then figure out, as I increase the temperature, how the number of vacancies increases as well. Kind of a final comment is talking about impurities and units. Impurities and units. Well, what I typically work in, and this is because I'm a person who thinks on kind of an atomic level, is I think about either an atomic fraction or a mole fraction. And for me, the reason I think in this term is because I think about chemical formula, right? Because I'm always thinking about things such as, say, barium, strontium titanate. Barium X, strontium 1 minus X, TiO3, right? So I'm thinking about the fraction of barium sitting on a strontium site in strontium titanate. And this type of fraction is simply the number of impurity atoms divided by the number of impurity plus the number of, we'll call this host atoms. Right? So if, we know that, say, 1 out of 10 sites, right, well, gives you 1 out of, 1 plus 9, 10th. Again, this is something that, for those of us who think in terms of chemical formula, it's a very intuitive way. People who like percentages, of course, you multiply this by 100 and you get 10%. Now, another way to think, which is equally valid, is weight fraction. And weight fraction, basically you take the number of moles or atoms, and we use Avogadro number, and well, use Avogadro number if you're dealing with the number of atoms, but if you're dealing with the number of moles, you can use the atomic mass to get the mass of impurities divided by the total mass, which is the mass of the impurities plus the mass of the host atoms, and then, times 100 if you want percentages. Now, this is very different from this, and when you're looking in the literature or you're reading a manual for a piece of equipment and they talk about dopants, defects, impurities, make sure you get the units right. This weight fraction is very useful in many situations, and where it's most useful is in production. Right? So, for example, you're working in a glass factory, right? And they bring in, silica glass in the form of frit, and they bring in phosphorus, and they bring in sodium in the form of soda lime, and you have to deal with the amount of impurities. Well, you're not going to take and weigh 2 tons of glass and then use Avogadro number and the formula weight of glass frit to convert everything over into atomic fraction, but instead you're going to say, okay, I've got 10 tons of silica frit, and I've got zero point 0.2 tons of soda lime. So what does that give me in terms of the total impurities that are going in? And that's going to be a weight fraction. So they're both useful. When I talk to you in class and you get problems from me, they're almost always going to be in atomic or mole fraction, because for laboratory scale work, and in particular those of us that are kind of theory oriented, that's what we think in. But do be aware that both your textbook and in your life as an engineer after school, you may equally see either one of these interchangeably depending on your application. So I will see you on Monday, and we're having a quiz on Monday.